Hello. In today's video on the kinetic theory of gases, we are going to discuss the Maxwell-Boltzmann distribution formula and the various forms of it for determining the molecular speeds of not only determining them but also discussing about the molecular speeds of the molecules of a gas. Now, as far as the kinetic theory is concerned, the basic postulates of the kinetic theory laid down in the previous video or prior to that is that the molecules of the gas being in constant motion, they collide with one another, and the collision is perfectly elastic. And during those collisions, they exchange energy and momentum with each other, and thus the kinetic energy of a particular molecule changes with time. And the number of gas molecules and the number of collisions taking place in 1 second, it is so large that the number of molecules belonging to a particular velocity range that remains constant with time. Now, Maxwell and Boltzmann, they came up with a formula which uh, tells about the number of molecules, the velocity that is carried by the molecules, and ranging in the velocity range from v to v plus dv. So they have set a particular range in which they want to know that how many number of molecules exactly possess the velocities lying in that range. And that formula is given as this. This is n times of dv, where dv is from the velocity range v to v plus dv. So it's obviously lying in that slot of dv. And that is equal to root 2 times pi n m, which is the mass of each molecule, is the same as predicted in kinetic theory of gases, and v squared divided by pi, k being the Boltzmann constant, T being the absolute temperature scale, and that to the power 3 by 2, followed by the exponential taken in negative. The negative power in the exponential carries mv squared over 2, which is the kinetic energy term, divided by kt. That can be given as E divided by kt. Never mind. And that all of that multiplied with dv, not there at the top but in the side. So that's more or less the formula, where we have described each and every term. In case you haven't followed, you can just recap and see for yourself. Now, if we are defining, obviously E is equal to half of mv squared, where it is the kinetic energy term. Now, with that, what we get is we can take the derivative of E with respect to v, then we end up with mv on the right hand side, because the 2 has been multiplied and the power has been reduced by a factor of 1, and that leads to dE being equal to mv dv, or I can put the dv over there and dv over there, and I divide this thing over here by mv. What that gives us? Well, this also gives us that we have v to be equal to 2e over m under root. So we use these values in the above equation, this value for v and this value for dv that we use that in the above equation, and what we end up with is the range of energy. So the number of molecules having the energy range from E to E plus dE is something of the form n. Now we can give a subscript over here for nv being the number of molecules associated with the velocity range, and here ne being the number of molecules associated with the energy range, which is in the range of E to E plus dE, eventually giving out dE. And so that is equal to 2 pi n. You can check for yourself by putting those values, and pi kt, that remains as such, to the power 3 by 2. This is E under root, and over here the exponential term carries the negative power of E over kt, as was the case previously, but had I not defined E over here, then I wouldn't have, I have not given there, so I write it over here instead of mb square over 2. So this finally gives dE on the right hand side as well. We also know that the kinetic energy is related to the momentum as the square of the momentum over 2m, mass of each molecule. And from that as well, if we take the case of the derivative of energy with respect to the momentum, then we have the form, or we have the equation to be equal to, the 2's get cancelled, obviously we are left with p over m, and from here what we get is p is equal to, or we can just use the value of E over there for p square over 2m, so we need not be concerned about that. So again we have a relation for the number of molecules which are lying in the range from p to p plus dp, which is the range of the, which is the momentum range dp. So the above equation changes to the momentum form, and we are left with root over of 2 pi n. Again, you can check this for yourself by putting the values that I've just provided at the line above, and this is pi mkt over 3 by 2, and p squared multiplied to the exponential term, which carries, instead of E we have p squared over 2m, but this is 2m kt, and this is dp. So all of that, this is p squared, I guess, yes. So all of that is available to us in the three forms that we have just discussed for the Maxwell-Boltzmann distribution of the molecule speeds of the molecules of the gas. So the first form being this one, in the velocity range v to v plus dv. Then we converted it to the energy range E to E plus dE, which yielded this form. And finally we ended it with the momentum range falling between P and P plus dP. So these are the number of molecules which have the corresponding, which lie in the corresponding energy, momentum, as well as the velocity range. Now with these things available to us, what we can consider is a fractional value which is equal to the number of molecules associated with the velocity term over n that is present over here. So n gets divided onto the left hand side, and we have the fractional value, the number of molecules that are possessing the velocity v, and as a result of that we can consider the variation of this number with the variation in velocity. Obviously the velocity changes, the kinetic energy as well as the velocity, they keep on changing because they are constantly under collision. So as a result of that, but nevertheless we predicted that most of the molecules will possess almost the same amount of velocity, which is the most probable case, the most probable velocity. And if we remember, we had obtained the expression for the most probable velocity. So after defining this fractional value, we plot a variation of this fractional value with respect to the velocity, and we can check for ourselves the the results. So here we have a plot where we haven't yet showed the plot. Here we have the velocity to be varying along the independent axis, and we have the fractional value to be in the dependent axis, and we can obtain the result from the above expressions, and what it gives us is a form like this. So this is more or less the Maxwell-Boltzmann distribution curve, giving the variation of the fractional value, that is the number of molecules, with respect to the corresponding velocity term. Now, if we consider the graph, we analyze that, and we come up with the maximum value that is possessed, and that is the most probable velocity term. So the most probable velocity term here is Vm. We had given it to be Cm. It won't really feel bad about giving it as Vm, but let's take it as Cm since we had discussed it like that. And then we have a slightly, not the much higher, but a slightly higher term. The average velocity C bar is slightly greater than the most probable case, and the highest value that we can have in terms of the molecular speeds, that being in this case being the RMS value, the root mean square value. So the order that we can obviously have is that the RMS value is greater than the average value, which is even greater or slightly greater than the value most probable case. So this gives the Maxwell-Boltzmann distribution in case of the velocity. As we have obtained the expressions for the RMS and the most probable as well as the average velocities, we need not be concerned about their values over here, but we just can see that the most probable case is the one where the number of molecules that lie are the greatest, because the most probable speed is the speed which is possessed by the maximum number of molecules. So that corresponds to that peak of that curve that we have in the graph that is available to us. So having discussed the Maxwell-Boltzmann distribution, we would probably stop over here, and because the next portion is going to be in detail, that is we are going to discuss about the degree of freedom as well as the law of equipartition of energy, if the case be. So that's it from this video. We'll be discussing the rest of the part related to the kinetic theory in the upcoming videos. Till then, thank you for watching.